All right, now we're starting to get into the examples that are laid out within the supplemental text that each of you should have by now. Now, we're going to do example 1 off page 15, and we're going to be looking at a series RLC circuit in which we're actually going to be finding the voltage across the capacitor through use of the substitution method. Now, for this one, we see that we had a switch that was closed in an upward position for t less than 0, but at t equals 0, we're going to actually allow for that switch to close down and then actually create a source-free RLC circuit in which we're going to basically get rid of the 100-volt source, and therefore we're not going to have any separate excitation that's going to allow for that voltage applied across the capacitor in its initial steady state to be held further on after the transient. Now, in this case, if we were looking for VC of t, the first thing that we actually want to do is find the initial conditions for t less than 0, and then also looking at t is equal to 0 plus. So, as we've stated before back in circuits 1, the initial condition for that capacitor voltage we can easily find by modeling that capacitor in steady state as basically being the open circuit. And for the inductor, we model that as basically being a short circuit. Now obviously if there's no change in the voltage, change in the voltage means that if that goes to 0, then the current's going to be equal to 0 for the capacitor. That's why we model that as an open circuit. And for the inductor, since the change in the current is going to go to 0, that's going to render that steady state condition of that voltage across the inductor to go to 0 as well. And if we look right here, we got the capacitor and the inductor in series with each other. And so the first thing that we can actually recognize is that the inductor's current is actually going to be equal to 0 amps for t less than 0 because it's in series with the capacitor being modeled and acting like an open circuit. So it's easy to go ahead and also find the voltage across the capacitor as well. So if we look here, this basically connection of that switch being closed in the upward position here actually puts that capacitor effectively in parallel with that 14.58 ohm equivalent resistance of basically 35 and 25 ohms together. Now, we just simply by voltage division can find VC of 0 minus, and that's just by voltage division, 100 times 14.8 over 14.8 plus 50 ohms, and that comes out with an initial voltage of 22.57 volts. And of course, IL of 0 minus is equal to 0 amps. Now remember, the voltage across the capacitor and the current through the inductor can't instantaneously change. So when that switch closes down and gets rid of this portion of the circuit and then connects up to the 10 ohm resistor, that voltage in that inductor, that voltage across the capacitor and the current through the inductor can't instantaneously change. And due to that, right when that switch closes down, that instance, right when it's closed down, that voltage value and that current value are both going to be the same because voltage across the capacitor can't instantaneously change and the current through the inductor can't instantaneously change either. I think I've said that 3 times now, but it drives home the point. So t is equal to 0 plus. In that case, VC of 0 plus is going to be equal to VC of 0 minus, which is 22.57 volts. And IL of 0 plus is equal to IL of 0 minus, and that's equal to 0 amps. Now for the change in the initial condition for the voltage across the capacitor, because we're going to be deriving a second order differential equation for the capacitor voltage, we're going to need that second initial condition, that change in the initial condition, basically the change of VC of 0 plus, that rate of change. Now again, we can't just look at this and just say, oh, we just take the derivative of a constant, take the derivative of 22.57 volts, and that just equals to 0. No. We're not doing that anymore. We've got to look at this as the change in the initial condition, the rate of change in the initial condition. And just by evaluating that current voltage characteristic at t is equal to 0 plus, and we see that that change in that initial condition is going to be equal to IC of 0 plus divided by the capacitance value. But because of the series relationship right here, the series relationship of the capacitor in series with the inductor, then IC of 0 plus divided by C is going to be equal to IL of 0 plus divided by C. And because the inductor's current is equal to 0, that means the capacitor's current at t is equal to 0 plus is also going to be 0. So that means essentially what's really going on here is that there's no stored current or stored energy in that magnetic field of the inductor. So when that switch closes down and gets rid of this voltage source, there's nothing that's actually, no current that's actually going to drive into the capacitor that would really invoke that type of rate of change. So we get 0 amps over 40 millifarads, which renders us a final rate of 0 volts per second. So just remember here that when you're finding these initial conditions, we don't just say, oh, the derivative of a constant. No, no, no. We actually have to go back and derive that. Because if that inductor had a magnetic field, once everything changes, that magnetic field starts breaking down, it's going to release charge into that capacitor and drive a rate of change. Now, let's go through and derive basically the differential equation and actually solve this problem. Now, this is the part that usually is the most intuitive for a lot of people. Once we actually get to the differential equation, like I've said before, that's where you guys should have practiced this over and over and over and over again. So that once you get to this aspect, you guys can just like start crunching and just like go on automatic, derive the differential equation, and then start solving it with a Laplace transformation. So let's take a look. All right. I'm actually really excited to actually be at Chattanooga State doing these videos because doing this from home was kind of hard with one whiteboard. So once that switch closed down, we had a source-free RLC circuit in which we had basically 10 ohm resistor, 1 Henry inductor, and then also that 40 millifarad capacitor. Now, if we look here, now the voltage here is defined from positive to negative in this orientation, and that's how we have to reference everything else within the circuit. But as we all know, inherent polarity of the voltage or across the inductor or for the resistor is really driven simply by the flow of current. But for this capacitor, we're going to orientate positive and negative from left to right, and we're going to stay consistent through our analysis. So by KVL, we have VL of t plus VRT plus VC of t, and that's equal to 0. Now, if we're going to utilize the substitution method, see, look at this. We have by KVL, that states that the sum of all voltages around that closed loop are equal to 0, or the voltage rises are equal to the voltage drops. Now in this case, though, we have one equation, 3 unknowns. So we have VC of t, so we want to leave that in there. So we go ahead and expand the inductor VL of t and also VR of t for the resistor for those equations to basically render L DIL of t dt, and then R times IR of t plus VC of t is equal to 0. Because of the relationship of the series elements here, IR of t is equal to IL of t is equal to ICT, because series elements have the same current. Therefore, that means that we can also say that these currents are all going to be equal to basically C times the change in that voltage, dVCT dt. And that's the variable we're looking for. So we're going to take this guy right here, we're going to substitute it in for IL of t as well as IR of t because they're the same. So we get L, and then we get dt dt, and then inner parentheses here, or inner brackets, C dVCT dt means we're going to basically take the derivative of the derivative. Right here we got R times C times dVCT dt plus VC of t, and that's going to be equal to 0. So once we actually go ahead and take the derivative of that derivative and also divide through by LC and put this into its standard form, we get d squared VC of t dt squared plus R over L dVCT dt plus 1 over LC VC of t, and that's equal to 0. And that makes sense because in a source-free RLC circuit, once all that energy is released that's been stored in that electric field of that capacitor, then we actually are going to basically burn all that up in terms of heat with the resistor, and then we're going to have nothing left for the voltage across that capacitor. So now, guys, we're at this point, and we go ahead and substitute in R over L. That comes out to be a value of 10. 1 over LC comes out to be a value of 25. And just looking at this, we can see that this is, in fact, a critically damped system because our two roots are the exact same. They're repeated roots. And so again, critically damped system, that means we are at that threshold where we have just enough resistance to basically prevent an oscillation from actually happening in that response. Now in this case, we're just right there, but if we took away some of that resistance, we're going to start getting some of that oscillation in there and have complex roots. But we got just enough here. So now guys, once again, you should have practiced this portion in deriving the differential equation, but this portion from here on out really should be automatic for you guys. Once you get here, you know, this is still conceptual over here because we're just deriving the differential equation from the current voltage characteristics of each element and also with the KVL equation. Now you guys, once you get that equation derived, you should start crunching. Just bam, work it out. So you take the Laplace transform of the entire equation, put everything in purple. This means that we're going to be in the frequency domain right here. And then we get s squared VC of s minus s times VC of 0 plus minus VC prime of 0 plus. That's what we had over there as the change in the initial condition, but I'm just signifying it basically with a little apostrophe right here. So, or we can sometimes say VC prime plus 10 times s VC of s minus VC of 0 plus 25 VC of s, and that's equal to 0. Now be careful, once we actually combine like terms of VCS over the left and take the initial condition portions and move them over to the right hand side because they're going to be more constants, then we have to make sure that we multiply through 10 times s VC of s, 10 times negative VC of 0 plus. And when we do that, we get essentially a characteristic equation over on the left-hand side, s squared VC of s plus 10s VC of s plus 25 VC of s. We move over to the right side, s times VC of 0 plus VC of 0 prime plus 10 times VC of 0 plus, which renders us s times 22.58 plus 225.8. So we go ahead and solve for VC of 0 plus. So we get the numerator is going to be divided by essentially that characteristic equation. And we can see that by factoring s squared plus 10s plus 25, we can factor that out into two repeated roots. So s plus 5 times s plus 5. And so now we go ahead in order to find, because remember we can't take the inverse Laplace transform of this just yet. We have to have it in the simple terms. Simple terms by partial fraction expansion is a over s plus 5 plus b over s plus 5 squared. And we know that when we take the inverse Laplace transform of both of these, it's going to be a times e to the negative 5t plus b times t times e to the negative 5t. So basically we're going to have only a transient portion of the exponential form for the solution of this type of system here for this problem. Let's finish this thing up. All right, so just as we've said before, guys, now in order to actually find A and B, find those coefficients, all we have to do is multiply through the denominator and then actually get an equation that we can actually develop two system equations. We have two unknowns, we need two equations. S times 22.58 plus 225.8 is equal to s plus 5 times a and then plus b. And then we evaluate that as s is equal to 0 and s is equal to 1. Remember, I don't care how you do this as long as it's right. We get two equations, 225.8 is equal to 5a plus b, and then 248.38 is equal to 6a plus b. We go ahead, put that into our matrix and get it into its reduced echelon form. And then we get a is equal to 22.58, b equal to 112.9. So here we got it, guys. VC of s is equal to 22.58, over s plus 5 plus 248.38 over s plus 5 squared. Take the inverse Laplace transform, and sure enough, guys, this is what we get. 225.8 times e to the negative 5t plus 112.9 times t times e to the negative 5t volts. From here, this is the first problem. We're going to finish up with the next three, so we're going to take a look at two other problems with the series configuration, in which we're also going to be looking at overdamped response as well as when we have basically the underdamped response when we see oscillation. So, see you next time.